Now, this picture is an important picture. Actually, this is taken from your textbook of banks, but I have given a different perspective to that processes. So this diagram, this flow chart, gives you the steps of a discrete event system simulation. So if you intend to develop a discrete event system simulation approach to solve a problem, these are the steps that you need to follow. So it consists of these steps of a discrete event system simulation project. In the first phase, we have 2 tasks here. In the second phase, we have a few more tasks to complete. Then we have the third phase here, and we have the fourth phase here. So these are the phases. In each phase, we have some tasks to perform, which we are going to study in detail. So we start with the discovery and the orientation phase. So in the discovery and the orientation phase, we start with the problem formulation and we set the objectives of the simulation study and the overall project plan. Now, in the model building phase, this is the phase that we are going to be mostly interested in the first place. Okay, this is maybe hardest of all these phases. We conceptualize or model of the system, and we also collect data from the original system at the same time. So these 2 parallel tasks are performed simultaneously, and they are interrelated with each other. Then we translate the model into a software environment. We verify that model, then we validate that model. And in the run phase, we create an experimental design because now we have a valid model to test things, to answer what if questions when we intend to apply some changes in the original system. We can make any type of experiment over the simulation model that we have, and then we run simulations and analyze the results. Sometimes the results cannot be too reliable due to huge confidence intervals, and in order to get more reliable results statistically, we may need to increase the runs of simulation. Either we take a longer simulation run or we can replicate the simulation runs. And once the results are obtained statistically, we document the simulation model that we have, and also we report the results. Documentation is important. I'm going to explain this later. And finally, we can implement the policy that we have determined as the optimal policy in the end of the simulation experiments. So we have 4 phases: discovery and orientation phase, model building phase, run phase, and implementation phase. Main focus in this course is going to be on the model building phase here. Now, we need to understand these steps one by one in the following pages. However, what I need to tell you is, if I ask you, what is the most important task? What is the most important process in these steps of a discrete event simulation project? Actually, the most important task is, my friends, validation. So we need to be very careful at validation. A wrong result in the validation process, assuming an incorrect model as a valid model, can create dangerous results. So validation requires so much attention, perhaps the most important task in all of these steps of a discrete event system simulation. And then we may say the second most important step can either be problem formulation or data collection. And I'm going to explain why they are the second most important, but the most important task here is the validation, and the most dangerous one. Okay, so let's focus on these tasks step by step and see. Let's start with the discovery and orientation phase, and we always start with the problem formulation. So it says in problem formulation phase, we need to define the problem that needs the solution, and we must understand that problem clearly. So why is that? Because, as I have told you, if you are going to create a model, a simulation model for the system that you are studying, the aspects of the system that you are going to introduce in the model is totally dependent on the problem formulation. So it's dependent on the problem that you are trying to study, which entities you are going to take from the original system as a part of the model? Which attributes you are going to record about them? So which activities you are going to observe, which events they are going to occur and change the state variables, and which state variables you are going to be interested in. All of them are dependent on the problem that you are trying to study. So usually the students who are interested in simulation modeling and who would like to have an undergraduate project about simulation, okay, they usually go to their supervisors and they say, we would like to do a simulation project. Then the supervisor asks, so for which system and what is your problem? Okay, what is your problem about which system? The students always say, we do not have a system or we do not have a problem, we just like simulation. Okay, so that is not how you should start a simulation project, okay? So there should be a problem about a system that you intend to solve, and if simulation is the correct tool to solve that problem, then you can use it. You cannot just go and perform a simulation project. Now, therefore, we need to understand the problem that we intend to solve. The next step is setting of objectives and overall project plan. So the objective indicates the questions to be answered by the simulation. So what is my objective? So for example, I am going to construct a new door or new entrance in my warehouse, and I want to see the performance change if I do that. So this is my objective. This is the thing that I want to answer. Or for example, between 2 p.m. and 5 p.m., how many cashiers I need to schedule in my supermarket? Okay, how many cashiers should work at that time? So this is the question that I would like to answer. So that is my objective. I am going to find the optimal number of cashiers that I am going to employ between these hours using a simulation methodology. And also I need to determine the overall project plan, and that overall project plan should include a statement of alternative systems. What are my alternatives? Am I going to work with a single cashier, 2, 3, 4, or 5 cashiers? These are my alternatives. And as I change the number of cashiers, I can also change the service policy through the cashier process. For example, I can spare a separate cashier for credit card payments or cash payments. Okay, this may be a policy. And I want to see the effect of that policy in the service time of the cashiers to the customers. And I need to develop a method of evaluating the effectiveness of these alternatives. So if you intend to try 1, 2, 3, 4, or 5 cashiers and a separate cashier line for credit card payments, I mean, there are 2 alternatives here and 5 alternatives over there. As a Cartesian product, there are 10 alternative systems here. We need to compare all of them one by one. And the project plan must have statements about the resource allocation as well. I mean, the simulation projects are long-term projects. They take some time to perform, and we are interested in how much money that we are going to invest in the simulation project, because we need to employ some simulation experts there. We need to collect data about the original system. So you are going to see each step, each following step here, and all of these steps require some attention, and they as well require some costs. Okay, and we need to allocate time for each of these tasks, and people, human resources, meaning the simulation experts here. Therefore, because this is a project, simulation development is a project, the project plan must also have statements about resource allocation. This is not just a rule of simulation projects, this is a general rule for all types of projects. So the second phase, and the main focus should be put on the second phase, is the model building phase. Now, in the model building phase, as you can see, there are 2 simultaneous tasks here: model conceptualization and data collection. Okay. Now, these are simultaneous. These are going to be performed at the same time almost. So let's start explaining model conceptualization. What is that? Essential features of the problem must be introduced in the model, and the basic assumptions that characterize the system must be selected, it says. So it says essential features. So how can I determine which features are essential or not? I can determine it by looking at my problem. So I'm going to determine which features are essential depending on my problem. Okay, so essential features of the problem must be introduced in the model, and the basic assumptions that characterize the system must be selected. So there may be some assumptions. For example, I have told you that the transfer of the gasoline supply into a gasoline tank or gasoline depot occurs instantaneously, but it is not true, right? That is just an assumption. I mean, if you are going to transfer a tank of gasoline into a gasoline depot, it is just going to take some time to fill it, right? For example, 1 minute or 2 minutes. But that amount of time is usually so small compared to the other activities of the gas station, right? Because of that reason, we may have an assumption here that the transfer of the gasoline into the depot is an instantaneous event. So this is just a basic assumption to characterize the system, but this is not true. So we need to determine such basic assumptions, because otherwise, if you do not determine such assumptions, such basic assumptions, modeling can be so complex. Now, in the model conceptualization phase, one important aspect is this: model construction is probably as much art as science, it says. So, I mean, you can be an engineer, a good engineer, and you can approach very scientifically to construct your model. But for simulation models, model construction is also art. Okay, so you should not think too complex. You should not think so much in mathematics. So it requires some expertise. Model construction requires some expertise. I mean, you can only get better if you try to construct models, new models and new models again and again. And after several tries, you can come to the perfection. So just like the art here. So we need to start with simple model and build toward greater complexity. I mean, in the first part of the model conceptualization, you should think simple. The system should be considered in very basic assumptions. Then, depending on the problem that you have in hand, you can introduce complex components into that model step by step, and you are going to create a much more valid model in that sense. Okay, this requires a process which adapts through calibration. Then we are going to abstract the essential features of our problem, and we select and modify basic assumptions that characterize the system, and then we enrich and elaborate the model until a useful approximation results. Okay, so when we are going to stop to make the model complex, when we get enough the approximate results, valid results from our model, as we are going to take from the original system. And we are going to explain how to do that in the validation parts in this course, which is going to be mentioned almost in the last week of this course. So when we intend to conceptualize the model, imagine this, that you are doing this in your mind, not in a computer environment. So model conceptualization means you are trying to create a conceptual model in your mind, okay, or on a paper, wherever. But we are not creating the model over the computer software at the moment. So this is just conceptualization. This is our perception of the original system with basic assumptions, true basic assumptions. Now, data collection is a simultaneous task that we need to perform as we conceptualize the model. And it is said by Shannon that there is a constant interplay between the construction of the model and the collection of the needed input data. So as we construct the model, we are going to discover that we need to collect a new type of data from the original system. And as we collect data from the original system, we are going to understand the system better. So we are going to change conceptual model in our mind. So we are going to say that we need to put some more aspects from the original system to the model as well. So they are going to affect each other. So with the collected data, you are going to understand the system better. So the model is going to be conceptualized differently. And as you construct the model, you are going to realize that you need more data that you are going to collect. Okay. So the required data elements change with respect to the complexity of the model. So the more complex model you create, then you are going to require more data elements from that system. And you know, it takes time and the data collection must start at early stages of model conceptualization. Okay, so data collection takes some time. If you intend to develop a probability model for the inter-arrival times of the customers to a supermarket, now you need to collect some data from the supermarket and you need to observe the inter-arrival times of several customers for an amount of time. Data collection takes some time. I have told you that the second most important task in a discrete event system simulation project is either the problem definition or data collection. Data collection is important because this is perhaps the longest task, longest. So you are going to consume so much time on that data collection. So as you require more data, you need to be spending more time on that. Because of that reason, to prevent the danger, you need to start as early as possible for data collection at early stages of model conceptualization, but you can only start data collection after defining your problem. Still, with the current technologies, with the big data systems and transaction processing systems, complex systems can collect a huge amount of data about the events. For example, in the warehouses, you can use global positioning system devices or RFID, radio frequency identification devices, to collect data about every event on every inventory item. Okay, so you can collect a huge amount of data and without spending a nickel. So because of that reason, nowadays the people are collecting a huge amount of data first. Then, if they are going to create a simulation model, they are taking the part of the data if it is necessary. But still, I should say that it is better to define the problem first and collect the data, because sometimes it may be too costly to collect these huge amounts of data, and collecting data that is unnecessary is actually a waste. So we need to be careful about this point. And as I have told you, another second most important task can be problem formulation, because you see, if the problem is not correctly defined, then the model that you are going to create is going to be an unnecessary model. It is not going to solve your actual problem because you have not correctly defined it. So you need to understand your problem carefully. So these two tasks are important, but the most important task is always validation. Do not forget about it. So model building phase continues with the model translation. And we say that real world problems require a great information storage and computation. Okay, so when we say computation, it means computation time. Now, if you are going to create a simulation model of a supermarket, you are going to construct it over a simulation software, and the simulation softwares give us many advantages. So what type of advantages they are going to provide? Actually, we are going to talk about this in the following weeks. So the model, the conceptual model in your mind, must be translated in a computer recognizable format. So you are going to translate that model in your mind to the mind of the computer. Why? Because in a computer environment, you can create much more faster simulations. Okay. Now, human mind is better to conceptualize things. Okay. From a computer, from an artificial intelligence, we are much better in conceptualizing things. I mean, we can easily, in a faster manner, understand what's going on in a complex system. We are good at these things. However, if we intend to make calculations, computations in the solution procedure, what I mean is running the simulation, the computers are faster than us. Okay, so if there is a well-defined algorithm that is needed to perform, computers can do it faster than us. But conceptualization of the algorithm is actually a task that is performed better by a human mind. So why we need computers? Because we want to run the simulation fast. So there are Arena, ProModel, Simulate, such simulation softwares where we can simulate the model that we have created, simulation model. And this part is called the translation, model translation. Now you have translated the model to the computer, but are we really sure that the conceptual model in our mind and the translated model in the computer environment are the same? Okay, so we ask this question. is the computer program performing properly? Is the model correctly represented or translated into the computer? Okay, so we have assumed some input parameters or distributions. So, for example, we have said that the inter-arrival times of the customers to the supermarket is exponentially distributed. But did the computer really understood that? In order to translate this fact to the computer, we need to have computer understand that model, right? So this is going to be tested by model verification. Okay, so we are going to check if the computer really imitates the conceptualized model in our mind. So if the conceptual model in our mind and the translated model into the computer really fit to each other. So this is called model verification. Once you verify your model, once you are sure that the conceptual model in your mind is properly translated into the computer environment, then you are going to validate your conceptual model. Okay, now that you can take simulation runs of your conceptual model because it is translated to the computer environment, now you are going to ask the second question: is the model representing the actual system behavior? So the translated model into the computer, which is a perfect version of the conceptual model in your mind because it is verified, but is it valid? Is it valid? Is it fully representing the original system? Because this is the actual question that we need to ask. Maybe the conceptual model in your mind was already incorrect. I mean, you have verified it in the translation process. The translated model is a perfect fit for the conceptual model in your mind. Maybe the conceptual model was wrong. Okay? Maybe you have conceptualized in your mind, unfortunately, incorrectly. Okay? So at this point, by using the verified model in the computer environment, we are going to check if the model is valid or not. So validation is achieved through the calibration of the model. Okay, we are going to learn about this in the last weeks of this course. Now, when you create a verified model for the first time, you will realize that the results that it has have differences between the results of the original system. So it's not a valid model. So there will be some discrepancies, differences between the real world results and the verified computerized model results. And these differences are called discrepancies. And these discrepancies help us to gain insight and improve the model. And as we calibrate the model, we improve it. And at some point, we are going to accept that it is a valid model. And the outputs of that model, verified model, is fully representing the outputs of the original system. And once we say that the model is valid, then we can say that the results of the experiments obtained in the runs of the simulation over that model are reliable. Okay, you can only say that they are reliable if you have a valid model. So therefore, we say that this step is the most crucial step, the most important step of the simulation, because an invalid model, unfortunately, can make us make wrong decisions about the true system, and it can yield erroneous results. Okay, so in that case, running simulations and making decisions with an invalid simulation model can even make things worse. Okay, so we need to be very careful at this point, and we need to be sure that the simulation model that we have created is a valid model and it represents the original system correctly. I'm not saying perfectly, but correctly. So a perfect representation is impossible. And the third phase is the run phase. At this phase, we create an experimental design. Now that we have a valid model, we need to determine our decision alternatives, and under each decision, under each different policy, under each different input variable, for example, the different number of cashiers to schedule, we are going to run simulation. We are going to make experiments on the system without disrupting the original system, okay, because we are making experiments over the model. So for each design alternative, we need to decide about the warm-up period. So we are going to learn about these warm-up periods and length of simulation results and the number of replications in each run. So what is the warm-up period? For example, if you are going to run a simulation in the supermarket, in order to imitate the original system, you are going to open it at 10 a.m., right? So at 10 a.m., the supermarket is going to start working in your model, of course, start working as an empty supermarket, but the main performance metrics are going to be observed when the supermarket reaches to steady state. So if you take the statistics in the observation of the overall time, you are also collecting some statistics from the beginning as well, where the system was empty. So we remove that warm-up period from our statistical analysis, and we are going to look at the statistical results in the steady state of the simulation, where the supermarket comes to a steady state with lots of customers and scheduled cashiers, so on and so forth. And also, we are going to determine the length of our simulation runs as well, because the longer the simulation runs, you get more statistical outputs. And with more statistical output, the estimates that you are going to calculate are going to be more reliable. And the number of replications of each run is also important, again, in order to build confidence intervals which are narrower. And in order to get central limit theorem to use to create confidence intervals, we need to have replications of the simulation runs. You are going to learn about this in the following weeks much better. So why do we have a warm-up period? Because we want to remove the bias caused by the warm-up period. So if you want to get unbiased statistical estimates, you need to define your warm-up period. And if you want to reduce the variance of your simulation results, then you need to increase the length of simulation runs and the number of applications in each run. Now, in the run phase, we continue with the production run and analysis. So we run the simulation replications and we analyze the statistical results. And then we use them to estimate the measures of performance for alternative designs. So for each alternative design, we run the simulation with enough replications to get reliable results. And here at this point, you see we have what? We have a decide module here. Do we need more runs? Yes. If we need more runs, then we add more runs. Or maybe you may think about changing the experimental design as well. Okay. So before moving further, I'm just going to show you these feedback loops here as well. After creating a conceptual model and create data, you translate the model into a computer software. Then you need to check if you have a verified model. Now, if the model is verified, it is not verified, then you need to create another translation of the model. Okay, if the conceptual model in your mind is not perfectly translated, then you go back to this step. However, if you have a verified model, then you need to ask the second question here. Is the model valid? If the model is not valid, this means the conceptual model in your mind is wrong. Okay? So you are going to go back to the model conceptualization and maybe the data collection as well. Maybe you will require a different type of data to collect. So after the validation step, if your answer is no, you go back to the beginning of the model building phase. So this is why model building phase requires so much focus. The other phases, especially the experimental design and running simulation replications, they are just taking so small amount of time. Now you see, if we need more runs, if we want to increase the accuracy of the performance measures or the statistical estimates of these performance measures, we are going to add more runs to our simulation. And then in the implementation phase, we document our simulation project. So it says program documentation keeps the model for future analysis and modifications. Why documentation of the simulation model is important? Now imagine you are working as a simulation expert in a global company and you are creating simulation models about some systems, for example, a supply chain system. So you have created that model and it's a very good model, it's a very valid model, and you have run many simulation runs on that. You have made very optimal decisions based off the simulation results. You are good at your job, okay? Now, you are going to leave that company for another purpose. Okay, you just want to be an actor, for example, or a singer. You are leaving the company and they are going to employ a new simulation expert. Now, is this guy going to create all these simulation models from scratch, or is he or she going to update your models for future studies? Okay. Now, if he or she is going to work with your models that you have created in your time, or update them for the future problems or future studies, then he or she needs to understand your model. Okay, and documentation is very important at this step. If you have a documented model, not just created with a software, but a correctly documented model, will help other users to understand the model. Okay, so that is the reason why documentation is important. And also we need to keep progress reports for the simulation project. So at which point the models are updated, which updates are made at which time. These kind of progress reports must be kept as well. And also we need to report the statistical results of the simulation as well. And after statistical results are reported, we can safely go to the implementation phase. And if we choose one alternative optimally, for example, employing 3 cashiers and with a credit card cashier separated, if we find this optimal with our simulation results, then we can safely, if our simulation model is valid, we can safely implement that decision between 2 p.m. and 5 p.m. And the success of the implementation phase totally depends on all previous phases here. Okay, all previous steps here. Okay, so that is the end of the first module, first chapter. We are going to continue with the next module. Please do your reading assignments, do your reading tasks explained in the exercise set and in the end of every module.